So let's start with the definition of self-balancing binary search trees. And so as we discussed in the last lecture, all operations find, insert, delete, find min, find max, successor, and predecessor all run in theta of d time in the worst case, where d is the depth of the binary search tree. Now in the worst case, the depth could itself be theta of n if basically your tree ended up being like a linked list. And this would happen if you insert in sorted order or reverse sorted order. But what we also argued, and I didn't prove this, but you can prove this by induction, it's not very hard. You can show that in any binary search tree with n nodes, there exists a node at depth at least log n. So in some sense, log n is the best you could hope for the depth of the tree. And a self-balancing binary search tree is one that always maintains a maximum depth of theta log n. So all the operations run in theta log n. These are more complex than simple binary search trees, and I will discuss the Avl tree, which is one such example, which I feel is conceptually is the easiest self-balancing tree. And it's easy enough that it's conceptually clear, you can understand it in a lecture, and homework 3 will be about coding up an Avl tree. So all operations can be done in theta log n. So this is like the ultimate data structure, because all operations, find, insert, delete, find min, find max, successor, predecessor, all run in logarithmic time. So it's a pretty amazing data structure. Now the key to understanding how an Avl tree rebalances, so rebalancing is an operation where it will, once the depth increases too much because the tree is getting imbalanced, it will rotate to rebalance. Now what is a rotation? So the rotation is the following operation. So here I'm describing some subtree rooted at x. X has a left child subtree called T1 where all the keys are less than x. Let's assume for the sake of this discussion that all keys are distinct. X has a right child y, and y has two children subtrees T2, and it has another child subtree T3. The keys in T1 are less than x, the keys in T2 are between x and y, the keys in T3 are more than y. What a rotation does is essentially it takes a node, takes one of its children and makes the child the parent, and the parent becomes the child. So their roles get switched. So x was the parent, y was the child. So this is called a left rotation. So you take the right child and you move it up. So it's moving to the left. Or actually I may be getting my what is a left rotation, what is a right rotation mixed up. So a rotation takes one of the children and moves it to the parent. There are two kinds of rotations, because you can take the right child and move it up, or you can take the left child and move it up, and these are different. And one is like the opposite of the other, and you'll see this over here. So let's just say we do a right rotation. So y will take the place of x. So y goes up. Now y has a left child that is x. And these subtrees, T1, T2, and T3 sort of rearrange themselves. And you'll see that it's really T2 that kind of switches its parent. That's right, T2 kind of switches its parent. So this is one kind of rotation. The opposite rotation, if you rotate from here, x would take y's place, and you end up at this tree here. So this is a rotation. An important point to note is a rotation runs in constant time, because all you have to do are just change a bunch of pointers. Coding this is, you have to be very careful, because you oftentimes when you code this up, you miss one of the pointers and then your code breaks. So you have to be careful when coding this. But if you write it out logically, you will see all the nodes that, all the pointers that need to be fixed. There is no change within any of these subtrees. This is a rotation. Sorry, just reorienting things. So any questions about what a rotation is? Okay. Now let me tell you about the Avl tree. So the Avl tree, so first I'm going to define something called the height of a subtree. The height of a subtree or a node, so technically you can also define the height of a node, the root of the subtree, or the maximum distance of a leaf. So this is one definition, or a maximum distance of a leaf to the node, and what I mean is the maximum distance of a descendant leaf. Right? So these two definitions are just the same. This is saying that you start at a node, you look at all of its descendants, you look at the one that's the furthest away, and that is the height. That is the height. That is the height of this node, also the height of that subtree, but we will assign the height to the node. Now, Avl trees are going to maintain a special height property for every node. They will maintain something called a balance factor. Now, the balance factor is the height of the left subtree minus the height of the right subtree, or it can be the other way around. They're both, effectively they'll be the same. I mean, it doesn't matter which one we use. So the height of the left subtree minus the height of the right subtree. Now, if the tree was perfectly balanced, then balance factors are always going to be 0. Because essentially everything is filled up on the left, everything is filled up on the right perfectly, and you have a perfectly balanced binary search tree. Of course, you cannot have a perfectly balanced binary search tree for all number of nodes. The Avl property, or the invariant, that is going to be maintained is that for all x, for all nodes, the balance factor is going to be -1, 0, or +1. So the difference in heights between the left and the right is going to be at most 1. Okay, the absolute value of this quantity of the balance factor is at most 1. So it's either 1 or 0. This is the Avl property. Now it turns out, you can prove this lemma, and again you can prove this by induction, that an Avl tree with height h has at least f of h minus 2 nodes, where f of k is the kth Fibonacci number. So what is the point of this statement? Why is this useful? What this says is, if you have height h, then using some formulas for the Fibonacci numbers, the number of nodes, as we say, is at least f of h minus 2, which is exponential in h, where the exponent is given by the golden ratio, or the base is given by the golden ratio. So the golden ratio is, approximately 1.6. One can look at further expansions, but it's 1.6. So this says that the number of nodes grows exponentially in 1.6. So it's not 2 to the h, which you would expect with perfect balance, but it's 1.6 to the h. What this means, you can flip this around and you can say, if an Avl tree has n nodes, what is a bound on the height? And that height is basically log of the base golden ratio of n. Right, log golden ratio of n, which is theta of log base 2 of n, because you can always do a change of base with just a constant. So if it was perfectly balanced, you would say it's log base 2 of n. Instead, you get log base phi of n. Now, phi is smaller, so log base phi of n is going to be larger, but it's still theta of log n. And this is how far we got. Are there any questions about this before I get into the actual construction of the Avl tree? I'm sorry, it's f. Yeah, this is badly written. It's f of h minus 2. That's what it should be. You mean why the golden ratio is appearing? So okay, so it turns out that the hth Fibonacci number is roughly the golden ratio to the power h. That's where the golden ratio appears, because there's a relationship between the Fibonacci numbers and the golden ratio. This is like some mathematical theorem that you can prove. that's not in some sense directly relevant to us. What's directly relevant to, okay, the reason why this is relevant to us is because, maybe let's step back a bit. What are we trying to argue? We want to argue that an Avl tree has small height. Right? That's what we want to say. And we want to say that the balance factors are going to help us maintain that. Actually, you know what? So forget it. Let me just prove this, and then maybe it'll be much more clearer. Okay, so we'll say an Avl tree of height h has at least f of h minus 2 nodes, where we say, you know, f of 0 is 0, f of 1 is 1, f of 2 is 1, f of 3 is going to be 2, and in general f of k is f of k minus 1 plus f of k minus 2. Okay, so this is what we're going to say, and then we'll just say that, you know, f of minus 1 is 0. We'll just define these for convenience. Okay? So really this is where the action really starts. So let's just understand the base cases. So we'll say when and it's convenient to say that, you know, we'll say when h is at least 2. Okay? So when h is equal to 2, the tree has, you know, at least one node. And of course, the tree has at least one node, and f of h minus 2 is 0, so the base case is true. Excuse me. So I'm just going to make this, I'm just going to say that I'm going to prove that it has at least f of h minus 2 minus 1 nodes. And you'll see that this is going to be convenient in my proof by induction. Okay, so now let's do the induction. Okay, so consider a tree of height h, where h is going to be greater than, let's say that h is greater than 3. Okay, so there's some Avl tree of height h. So how many nodes? Okay, so let's just say that the height over here is hl, the height over here is hr, and the actual height is h. Okay, so how do you write hl and hr with respect to h? What is h with respect to hl and hr? There is no log here. Why is there a log? How do you express h with respect to hl and hr? Plus 1. Plus 1 of what? Plus 1 of hl or plus 1 of hr? Of the maximum, exactly. So this is just the max of hl, hr, plus 1. Okay. Now, by the induction hypothesis, the number of nodes is at least 1. It's actually equal plus, okay, so let's just say that number of nodes is equal to the number of nodes plus number of nodes in L plus number of nodes in R. Right? Now I use the induction hypothesis. So I use the induction hypothesis, say this is 1. This is going to be HL and HR, which we just argued was the Fibonacci number of HL minus 1 plus the Fibonacci number of HR minus 1. And this gives you F of HL plus F of HR minus 1. Okay, so far so good? Okay. Now, there are two cases. Case 1, HL is equal to HR is equal to H minus 1, where both of these trees have exactly the same height. Okay? In this case, we'll say the number of nodes is greater than or equal to F of H minus 1 plus F of H minus 1 minus 1. Right? Now the Fibonacci numbers are a monotonically increasing subsequence, monotonically increasing sequence. So I can certainly write this is greater than or equal to F of H minus 1 plus F of H minus 2 minus 1, which gives me F of H minus 1 as desired. So there are technically 3 cases, but 2 cases one can fold together. Suppose HR and HL are not equal. Now what? Now we use the Avl property. So what is the difference between HL and HR going to be? At most 1. And in this case, it's going to be exactly 1, right? Because if the difference was 0, then we're in case 1. So in case 2, we have that HL is equal to H minus 1 and HR is equal to H minus 2, or the other way around. This is the Avl property here. This is where I use the fact that this is an Avl tree, so the difference in heights can be at most 1. So it's either H minus 1 or H minus 2, or the other way around. The proof is identical in both cases. Because if they're equal, we already know what to do. So now how many nodes are there? Now the number of nodes is at least F of H minus 1 plus F of H minus 2 plus 1, but this is exactly the Fibonacci recurrence. And that's the end of the proof. So the proof is done. Proof is completed. Maybe that sort of demystifies how the Fibonacci series enters the picture. It enters the picture because you have some series where, because of the Avl property, the number of nodes is essentially one previous term in the series plus the next previous term in the series. And the series that sort of is built from there is the Fibonacci series. Is that clear? Like, any questions about that? Hopefully that demystifies where Fibonacci numbers are coming in. In some sense, the Fibonacci sequence really seems to capture the number of nodes in some way. But this was not the plan. But if this is of interest, then we can continue talking about this. Okay, any questions? How the plus one, which plus one? This is technically, I'm sorry, this should be H. Mine looks like an N, but it's an H. But anyway, go on. Yes. Sorry, that was a typo on my part. That was a typo. Sorry. It should be -1. My apologies. You're right. It's a -1. Yeah. I was basically using this formula here. Yeah. Okay, any other questions? Okay. All right. So let's let's flow with this for now, and let's talk about this, because this seems to be of interest, right? Okay. So what we get is that an Avl tree has at least f of h minus 2 minus 1 nodes, right? So the -1 that you have over there is only there for it's to get the induction to work. So the question now is, so I'm just going to rewrite this. What do we want to know? We want to show. Sorry, let's get another piece of paper here. So we want to show that the number of nodes in an Avl tree grows exponentially in H. That's what we want to show. Now we know that the number of nodes in the Avl tree of height h is at least f of h minus 2 minus 1. So we want to understand how this quantity grows with h. So one thing you can do is you could plot the Fibonacci numbers and you can just see what's happening. Let me give you a quick and dirty proof that the Fibonacci numbers are growing exponentially. This is not going to give you the optimal growth rate, which is given by the golden ratio. But in general, we can do the proof. I'm just sort of thinking about whether I could just directly do the proof of the Fibonacci, about the Fibonacci numbers. Let me give you a quick and dirty proof. Let's not do that. Okay, so what is f of h? So f of h is f of h minus 1 plus f of h minus 2. Right? Okay. By the monotonicity of the Fibonacci sequence, right? So we know that this is at least f of h minus 2 plus f of h minus 2. So this is at least 2 times f of h minus 2. So it says that if you jump 2 steps in the Fibonacci sequence, you double the number. So when you look at powers of 2, the next number is twice. So with the Fibonacci, it's like you have to go 2 steps and then you get twice. This is an upper. This is it's a weak lower bound. You can do better than this. You can get the golden ratio. You can get things with the golden ratio. But let's just do this for a quick and dirty proof. So then, by induction, you can see that f of h is at least 2 to the h divided by 2. Or another way of saying it's like root 2 to the power h. Right? So this is saying this is like 1.4 to the power h. So what this says is that the Avl tree is growing exponentially, as it's at least growing exponentially with 1.4. A more careful analysis of the Fibonacci sequence itself gives phi to the h, where phi is the golden ratio. And it's a beautiful piece of math where the golden ratio is related to Fibonacci, but for our purposes it really doesn't matter that much, because once we get this bound, we know that if the tree has n nodes and the height is h, so we know that the number of nodes is at least f of h minus 2 minus 1. So this is going to be at least 1.4 to the h minus 1, and this is n. You move things around a bit, you get that h is at most log base 1.4 of n plus 1. Again, this is a crude proof. You can do a little better than this, but this proves that h, I'm sorry that my h looks very close to the n, my apologies. So the height is at most this, which, you know, by change of base, you can do as log base 2 of n plus 1. Right? So you can basically do a change of base times log 1.4 base 2. And this is just some constant. And so this gives you, this is O of log n. Okay, so this is sort of showing you how the Avl property and the Fibonacci numbers and everything gives you a height of log n. This is a very quick and dirty proof. Any questions about this? It's not going to come in your test, so don't worry about it. Just try to understand it. Mm-hmm. The reason, you mean why does the golden ratio appear? I mean, the golden ratio comes in for a more subtle reason. Like, you basically have to look at the limiting behavior of the ratio of these, and then the golden ratio pops up. It's a more complicated piece of math. I think you should, if you just understand this piece of math, which is like quick and dirty, but it immediately tells you why Avl trees have logarithmic heights. So what is remarkable is that this one property over here, just getting the balance factor to be either minus 1 or plus 1, leads us to the Fibonacci series. And once we have the Fibonacci series, we can prove that the Fibonacci series grows exponentially. The thing is, we don't get the optimal base here, but this is good enough for whatever purposes we have with the big O notation. I'll pause here and take any questions that you have about this. How does which part work by this one? Oh, so actually you prove this by induction. So what you get is that you get f of h is 2 times f of h minus 2, which will give you 4 times h minus 4 times 8 minus f of h minus 6. And you keep following this down and you'll get 2 to the h over 2. Because every time you move 2 steps in the Fibonacci sequence, you double the number. That's what it's saying, right? If you increase 2 steps in the Fibonacci sequence. So this is saying f of h is at least 2 times f of h minus 2. Right? And this is going to give you 2 squared times f of h minus 4, which is going to be at least 2 cubed times f of h minus 6. And you keep continuing that, and you'll end up with f of 2 to the h over 2. Not in half. No, it's not half. It's decrease the height by 2. Or increase the height by 2. Every time you increase the height by 2, you double the number of nodes. Exactly. And so you increase the height by 2, you double the number of nodes. And increase the height by 2, you double the number of nodes. So in a perfectly balanced world, when you increase the height by 1, you double the number of nodes. Right? That's what happens in a normal binary search tree, effectively. When you increase the height by 1, the number of nodes essentially doubles. And here it's saying, well, the number of nodes is going to double every time you go 2 steps. So on the average, it's like when you increase the height by 1, it increases by root 2. It increases by 1.4, 1.414, whatever. Okay. Any questions? I hope this was useful. I don't know. Maybe let me just poll you and ask, like, was this useful? Red for yes and green for no. I mean, this. So, green for like no, this didn't make sense. But red is yes, this was useful. So, just want to understand, whether you follow what's going on or not. So, okay, it seems somewhat split. Actually, it's a little weird. After all of this talk on the elections, one is getting used to seeing these bars of, like, how many people have voted one way or the other way. That it's a little strange, but yeah, okay. So it seems that it's somewhat 50-50. Like, some of you liked it, and some of you didn't. So I think again, the point is, don't get too hung up on the proof itself. If there's just one message you want to take away from this, that is just this message at the end, that if a tree, the Avl tree, I should say, the Avl tree has n nodes in height h, and the height is log n. That's what you need to take away. If you wanted to understand why that was the case and how it's related to Fibonacci numbers, then you would get into these two lemmas here, or rather this one lemma here, which says that the Avl tree of height h has f of h minus 2 minus 1. And the h minus 2 is simply just to get the base case to work. After that, it's just the Fibonacci recurrence. And you see that the Fibonacci numbers are so naturally associated with the Avl analysis because of this case, right? Because when the difference of the heights is exactly 1, which is the case when it's not imbalanced, you get that the left height is h minus 1 and the right height is h minus 2. Then what you want is a series which exactly has this property where you sum up the term for h minus 1, the term for h minus 2, and you get the term for h. And that's exactly the Fibonacci series. And that gives you this. And what is remarkable and sort of incredibly beautiful, if you think about it, is that people studied the Fibonacci. I mean, Fibonacci is from what, maybe 15 or 1600s? And they were studying, just these sort of abstract mathematical problems, and come all the way to 50 years ago, when we're trying to build optimal binary search trees or balanced binary search trees, the Fibonacci numbers pop up naturally as the mathematical tool to analyze, which is pretty mind-boggling when you think about it. Okay. With that, let's now talk about how to actually maintain an Avl tree. So any further questions? I haven't been looking at the chat carefully enough. So if there are any questions that are popping up, all right. So now let's go ahead and understand how we're going to maintain the property. So how to maintain the Avl property. So insert or delete like a standard BST. Okay. And one of the nice things you'll see with Avl trees is that it really doesn't matter whether you insert or delete, like all of it is just going to be the same analysis. So what is going to happen? So now let me ask you a question. when you insert a node in an Avl tree, so height is h, nodes are n. For how many nodes does the balance factor change? For how many nodes does the balance factor change? Okay. Is it a constant? Is it O of h? And remember, this is basically, again, just, this is log n. Log base 2, whatever, it's theta, right? Or is it many nodes? Okay, that's the question. For how many nodes does the balance factor actually change? Okay, so I need to run my poll. Relaunch the poll. Okay, so what does this question mean? It says you insert a node in the Avl tree. Now remember that the balance factor, if you recall, so the balance factor is the height of the left subtree minus the height of the right subtree. Right? So the difference between those is the balance factor. So when you insert a node, there are heights that are going to change. For how many nodes is the balance factor going to change? So there seems to be some confusion on this. So half of you seem to have got it right, and the other are split evenly between theta 1 and theta log n, theta n. So let me explain why this is the case. So imagine you have an Avl tree. And you insert a node somewhere. So you insert this node. The only nodes whose height changes are the ancestors. So the heights change only for the ancestors. No other node has a height change. So, but potentially all of them could get a height change. So it's really theta of h. It's theta of h in the worst case, I should have said. In the what is the largest this is. Okay? So this says that when you insert a node, the heights are going to change for this entire path to the root. But nowhere else does the height change. Like if you look at a node here, whose subtree is down there, the height does not change there. If you look at any other node, the height does not change. But for this path, for all the nodes, the height changes. So let me just restate that. I'll say that when a node is inserted, the heights change only for ancestors of the inserted node. And there are at most O of h such nodes, because that's the maximum height of the original tree. right? Or which is, as we said, is O of log n. So there are only logarithmically many nodes where the heights are changing, and that's the only place where the balance factor changes. The same is true of a delete. You have to think about it. The same is true for delete. So the point is, when you do an insert or delete on an AVL tree, the problem is it's not an AVL tree anymore because it doesn't have the balance factor property. So remember, the AVL tree, this is an AVL tree. An AVL tree is a binary search tree that has this property. This property is lost when you insert or delete. This property is lost when you insert or delete. And so the strategy now to fix is, so this is the basic algorithm. So you insert, delete like a standard binary search tree. You find all nodes where the balance factor is not in -1, 0, or 1. And these are all going to be ancestors of a modified node. And I say modified because it could either be an insert or a delete. And then what you do is, for each node, you fix the problem. And so the question, of course, is how are we going to fix the problem? And that is sort of the key of the AVL tree. The key of the code in the AVL tree is that there's actually going to be a procedure that is going to fix the problem. Okay, now let me ask you another question. After an insert or delete, by how much can the balance factor change? How much is it going to change by? Is it going to change by a constant? By now you'll know that the options are all the same. Is it going to change by logarithmic, or could it change by linear? So which of these are actually, by the way, if you need to ask questions, feel free to sort of stop me and ask questions even while the poll is running, and I can explain. When you insert or delete, how much can the balance factor change? So let me again just draw this picture so you can see what's going on. So maybe just think of an insert. So you go here, and now you've inserted this one node. How much can the balance factor change? So let's say you take a node, its balance factor is going to change. By how much is it going to change? Is it going to change by a constant? Could it change by a log? Or is it going to change by theta of n? Exactly. For a single node, yeah. Yeah, change for a single node. For a single node. Not the sum, but for a single node. Thank you. Yeah, that does make a difference. That makes a difference. So it only changes by a constant. And actually, you can even tell me what that constant is. How much is it going to change by for a node? 1. It's only going to change by 1 because heights only change by 1. Heights only change by 1. Either add or subtract depending on insert or delete. So the balance factor, which is a difference of heights, changes by at most 1. So this is actually really nice now. So our problem, so let me pull this slide up again. So I said for each node you have to fix the problem. So what is the problem? The problem is that the balance factor of a node becomes 2 or minus 2. Because if it's 0, 1 or minus 1, then there is no problem. So it's either 2 or minus 2. And what we'll see is there's actually going to be a series of tree rotations which will fix this problem. So when it's minus 2 or plus 2, we'll do some rotations to get it back to minus 1 or plus 1 without affecting any other trees. And so what we do is we actually fix the problem bottom up. We fix the problem bottom up. I'm not going to write pseudocode for this because the pseudocode actually ends up being fairly complex. Instead, I'll draw pictures and explain the basics to you. And if we have time, we'll walk through the visualization that I've given on the website. But if not, if I don't have time, please use that visualization. It's very useful for understanding what's going on. And if you look at the Wikipedia page, there's actually fairly detailed pseudocode for the Avl tree. Okay, so now we're going to fix this problem bottom up. What is the problem? So suppose a balance factor is minus 2 or plus 2. Both of these, they're going to be analogous to each other. So what this means is that the height of the left subtree minus height of the right subtree is minus 2. Moving things around, it's just the height of the right is equal to height of the left plus 2. We'll fix the problem bottom up. And because we're going to do it recursively bottom up, we'll assume that all strict, so I'll say for the balance factor of a node X. So assume all strict descendants of X have a correct balance factor, and the correct balance factor is in minus 1, 0, or plus 1. Okay, so any questions at this point? I'm now going to show you how to fix the balance factor at X. Any questions? Okay. So now we have two cases to handle here. So let me do case 1. So there is a node whose balance factor is minus 2. The plus 2 is actually going to be a separate case, but it's going to be like a mirror image of whatever I draw. So here's this node X, and its balance factor is minus 2. So the height of the right is 2 more than the height at the left. So I'm just going to keep track of heights. I'm going to call this is like, just think of it as, I just want to mark this off as saying I'm going to start my heights at 0. So there's some left subtree here. I'll call this T1. And its height is h, right? So going down from there, we'll say the height is h. Now this tree has a height, so, right? So this is h. So I'll say this is 1 going up to h. Now, let me show you what case 1 is. So case 1 is that this tree, which we'll call T3, is going to go up to h plus 2. And this tree over here is going to go to h plus 1. Or it may even go to h plus 2. This is the first case. Now, in the first case, the right child of y is going to be sort of the highest one. I want to draw another picture which cannot happen, and I want you to understand why that picture cannot happen. Why can't the following happen? This is x. So this is T1 going up to h. This is y. This is T2 also going up to h. This is h plus 2, and this is T3. And I'm saying this cannot happen. Okay, I'm going to pause here. I want to give you a couple minutes to see why this cannot happen. Just to fit on the paper. Just to fit on the paper. The important thing is not the area of the triangle, but rather the height. No, it has nothing to do with the rotations at this point. So why can't this happen? And actually here, you have all the information that you need. There's an Avl tree. Why can't this happen? Which would be 2 more than T1? No, we assume that there's actually a problem at x. So there is going to be, the height of the right is going to be equal to the height of the left plus 2 at x. I should say this is all at x. Exactly. So the thing is, we assume that all strict descendants have a correct balance factor because we're fixing the problem bottom up. So this cannot happen, because if this happened, then y has a problem. And we would go and fix y before we fixed x. So the idea is you're going to fix bottom up. We assume that all strict descendants have a correct balance factor. So we cannot have this situation. We are in this situation. There are more cases, and we'll go over the other cases. But I want to make sure that everybody understands this. And please ask me questions if it doesn't make sense. Do you see why this cannot happen? That is saying, yes, every subtree in an Avl tree, that's correct. Although the issue is, after the insertion, we don't have an Avl tree. We don't have a strict Avl tree, because there are places where there are errors. But what we're saying is, we are going to find a point such that no descendant has an error. And obviously such a point exists, which is the lowest point which has an error. And we'll sort of fix it going upwards, going up the tree. So the right picture cannot happen, because then the balance factor, the absolute value of the balance factor here becomes 2, which cannot happen, right? We assume that all strict descendants have a correct balance factor. So this is assuming that T3 is the highest one here. We are in this situation, not this situation. This folds two cases into each other, but they're both going to be the same, which is T2 may go up to h plus 1, or it may go up to h plus 2. And you'll see that that's not going to be a problem. Now the fix for this is we're just going to rotate x to y. We're going to rotate x going to y, and you see once we do this, the problem will be fixed. Once we do this, the problem will be fixed. So I'll draw this picture again in the next page, and I'll show you how that's going to get fixed. Actually, maybe there. So here, you see what's going on here. So let me do the rotation. So rotate y to x. What's going to happen is that y goes there, x goes there, x is going to have t1. So let's just keep track of the heights now. So this is now at the 0th position. This is at position 1. And so this is going to be at position h plus 1. Right? It's going to actually move down. It's going to move down. This subtree, the T2 subtree, is actually going to stay at its height. If you think about what's going to happen at T2, so now y, okay, so there's that, and then there's going to be T3 is going to be there. So T3 is going to move up, right? Because y moves up by 1, and y is going to pull T3 along with it. Sorry, my pictures have been drawn poorly here. Sorry, so this, let me just redo it on a separate page because I don't want it to get messy. So rotate y to x. So here's y. Was at height 0. Here's x. X now moves to 1. X is going to have a child subtree T1, which is going to be at h plus 1. Now what's going to happen to T3 is T3 is going to move up. And because it moves up, T3 is going to be at h plus 1. So I'm just going to draw that over there. Right. T3 is going to be at h plus 1. Now what happens to T2 is you'll see that T2 does not change its height at all. This pointer is going to sort of flip and go over there. So T3 is going to be at either height h plus 1 or h plus 2. Right? So T2, I'm sorry, is going to either be there or it's going to be there. So T2 maintains its height, T3 goes up by 1, and T1 comes down by 1. And now all the balance factors are fine. So the balance factors are fixed. Because we know that within T1, T2, and T3 there is no problem. This is by assumption. There is no problem in X anymore because the difference between this is at most 1. It's either both of them are the same or it's 1. And of course in T3 there is no problem. And in Y there is no problem because here it's going down to h plus 1 and here it's going down either to h plus 1 or h plus 2. So again the difference is 1. So the key is that there was something at h plus 2 and h. This was giving you the problem of the difference of 2 and they're both moving to each other by the rotation. Is this clear? Any questions? I'm sorry, say that again. You mean this case? You mean how can that happen? Well, it could happen because maybe this originally had a height of h plus 1 and you inserted a node and that made the height h plus 2. You're saying that no, what could happen? Oh, you mean that there would have originally been a problem over there? Well, okay, I'm sorry. Then the other case would have held, right? So there is that you inserted into T3. So maybe T3 had a height of h plus 1, and when you insert into T3, then T3 has a height of h plus 2. You shouldn't imagine that all of this is filled up. There could just be one node over there. The insertion could have actually made the height of T3 go up by 1. Questions? Is that clear? Yes? Okay, so that's a good question. So what you'll have to do when you code this up is that every node actually stores the height. And every time there's a rotation, it has to update the height. You would only go and rotate for those. Right? Yeah. And actually, as I said before, remember we said that when a node is inserted or deleted, the heights only change for the ancestors of the node that is inserted or deleted. So you actually know exactly where those nodes lie. No, it's not, because if this was at h plus 2, if T2 was at h plus 2, then you still have an imbalance here between h plus 1 and h plus 2. It could be at h plus 1 or h plus 2. I said both of these cases could hold. Because we know that the height of this at y is going to be h plus 2. But it could be because of both T2 and T3 or just because of T3. So just to reiterate, case 1 is that T3 is the highest. That's the case that we're looking at. I'm sorry, you won't be able to see this. T3 is the highest. This is the case that we just solved here. And in the other case we'll look at is that T2 is the highest. And then we'll again see that there's a series of rotations that fixes that problem. So now let me show you case 2. So case 2 is that T2 is the highest. So again, we'll go back to our picture here where this is x. We said this is at height 0. We have T1, that's at height h. You have y, this is at 1. This is T2, and this is going to be at h plus 2. And we have T3, which is at h plus 1. So I said T2 is the highest, and this is the case we're in. So again, you have height h here, and you have h plus 2 on this side, and this is the imbalance. But within this, there is no problem. And as we discussed before, T3 has to be at h plus 1. It cannot be at h, otherwise there's a problem at y. Now let me ask you a question now. What about this case? H T2, this is h plus 2, T3. What if both of these are at h plus 2? What about this case? Why am I not considering this case over here? Not necessarily. I mean, one doesn't know at what, the thing is you do an insert and then you keep doing these switches, so you don't know where the tree lies. It might not be the case, right? Because it could be that maybe there was a deletion somewhere. So maybe this is at h plus 1 and you deleted. You'd have to insert, but in case of a delete, you could end up at a situation like this. Okay, so tell me, why would this be okay or not? Okay. There's a problem because the height here is h and the height here is h plus 2, so there's a problem. So the balance factor is 2, which is not okay at x. Yes, good. So this is already done in case 1. Remember, in case 1, this is a picture that I had where I said T2 could go up to h plus 2. Right? So this is already this case. This is the same as this case. When T2 goes to h plus 2, I've already done this case. If T2 goes to h plus 1, then I've solved it. So this is actually already handled in case 1. So the thing we need to worry about is that T3 is actually shorter. Okay, so this is done in case 1. This is actually done in case 1. The solution here turns out to be kind of interesting. Is you actually have to do a double rotation. You have to do one rotation then another to fix the problem. So actually we're going to have to open this up a little bit more to understand, to get to the solution. So let me draw this out now again with x. That's at 0. So again, just to be clear, the sizes of the trees don't matter. It's really the height. Like the area doesn't matter in what I'm drawing here. So there's T1. That's at h. Okay, so that has a child y, and that's at 1. And I'm going to kind of draw this out where this is T3, and that's going up to h plus 1. Now this is z, so I'm going to sort of splitting it up even more. And what happens with z is now z is going to have 2 child subtrees. Now let's, right, so let me sort of draw these out. This is h plus 2. This is h plus 2. So this is just showing you what's going on in here. It could be that one of these is going up to h plus 1. So one of these could potentially go up to h plus 1 as well. But one of them definitely goes to h plus 2. Sorry, there. Right, so one of these has to go up to h plus 2. And so what we're actually going to do is we're going to do a series of rotations. We're going to rotate z to y. And then once we do that, then we're going to rotate from there to there. And that's how we fix the problem. So this is the important picture to remember, that this is the way we're going to fix it. Even if you don't follow what I'm doing right now, if you go and do it yourself, you'll see how to fix the problem. So these are the pictures you need. And you need to understand this because you're going to have to code this up for homework 3. So homework 3 is on Avl trees. So let's just go ahead and do one of the rotations. So let's go z to y. Let's first do that rotation. So x, that stays at 0. And t1, that's at h. Now here's y. I'm sorry, so this is going to become z. Right? Z is moving there. That is going to send it to y. And T3 is going to drop by 1. So T3 is going to end up at h2. h plus 2, I'm sorry, t3, that is going to end up at h plus 2 because we're going to rotate z up, and so y moves down. Now whatever tree was here is going to move up by 1. Whatever tree was there is going to move up by 1. So that is going to be so this is t2 and t2 prime. So this is t2. Now t2 could either move up to h plus 1 if it was h plus 2, or move up to h. It could move to either one of those depending on what the tree was. And this tree, whatever it was, is going to stay where it is. This tree is going to stay where it is. So now you have a situation where the highest tree is on the right side of z. And this is basically case 1. This is case 1. And you can go through the various situations and you can see it, and you will see that it's basically, it's case 1 all over again. So this, it requires some care to work all of this out. Okay, so I'd recommend that you go back and you do it. And if you're in this situation, you'll see that it's back to case 1. So are there any questions about this? It's a bit like you have, like, at some point I can keep drawing these trees, but the best way to do it is to go back and to try these out yourself. And when you then do this rotation, you will start fixing the problem. Okay, so this is really when you're in this picture here. So you rotate this root up there. If I can do an example, it's easier for me to actually do just to do a visualization. Like, let me see if I can get that up and running. So let me stop the share. And let me instead okay, does everyone see the screen here? Yeah. So this is inserting. Hang on. I need to maybe slow it down a bit if I can. Okay. Okay. Now I insert 10. I'm going to insert 20. Okay. So you can see that the heights are being maintained. The heights are being maintained. So it's actually starting the heights at 1 as opposed to 0. So this is saying the height of that is 1. The height of this tree is 2. So now let me insert 30. Now you'll see there's going to be a problem with the balance factor. Okay, so it's going to go down. It's going to insert 30. Right? And then it's going to update the heights. It's going to say the height is now 2. And the height of this is 3. And now there's going to be a rotation to fix the balance factor. So maybe let me skip back a bit. So when you insert 30, what's going to happen is that the balance factor of the child is going to be, actually the balance factor of the child is going to be okay. The balance factor of 2 is going to have of 10 is going to have a problem, right? Because the height of this side is going to be 2 more than the height of this. So what it's now going to do is going to rotate this to the root, right? And that rotation is now going to fix that. And so now let's insert 40. And when you insert 40, at this point there's no problem because the height of the subtrees are going to still have a difference of left and right are still going to have a difference of 1. But if we insert something over here on this side, we're going to have a problem. So let's say I insert 35. So then 35 is going to end up down here. Then you'll see that there's going to be a double rotation to fix that.